So moving on to electric circuits, we need to understand these three absolutely fundamental ideas: current, potential difference and resistance. Before we get on to the complicated sort of circuits, we really need to understand these basic key terms. This is really the language that we're going to use to describe what's going on in circuits, and if you're not clear about what these three things mean, then you're going to find the rest of this quite difficult. So do spend some time, think about it, work your way through, see if you can work out these three different concepts, what they mean. We're going to look at what current is and how we measure it. We're going to look at potential difference and how we measure that and what it means. And we're going to look at resistance and how it links the other two quantities together. So first up, we need to understand what electrical current is. Well, a current is the rate at which charge flows around a circuit. So if you've got charge from static electricity, these charges, instead of being static, are now flowing around a circuit, and the rate at which they flow around a circuit is the current. Okay, just to confuse you a little bit, we use the symbol I for current because we use C for other things. We need to know the basic stuff. Current's measured in amps. The thing we need to use to measure it is called an ammeter, no P in there, notice. And when we connect an ammeter in the circuit, as you'll see, we need to put it in series with a component. Trickiest bit of this is to work out how these three things are linked together. So the charge that flows around a circuit, if you think about it, this is the current times the time. Because if the current is 3 amps, that means there's 3 coulombs going past per second. So if we do 3 amps for 10 seconds, 30 coulombs of charge have gone past. Symbols for that: charge is Q, current I, times T for time. Just notice, as always with time, the standard unit of time is seconds. So if they give you a time in minutes, be careful that you turn that into seconds before you do the calculations. Here's some simple circuits, just to show you the idea. So here's a circuit, it's just got one bulb and a battery there giving us 10 volts. First thing to notice is the current on both sides is the same. If there's one crucial thing to understand above all others with current, it's that the charge doesn't get used up. So the current that's going into a component and the current that's going out must be the same. It's got nowhere else to go. The charges just go through and round, back to the battery, back to the bulb, back to the battery, back to the bulb, round and round. Okay, notice this one, if you've got 2 bulbs in this circuit now, 1, 2 bulbs. Okay, again, the current is the same all the way around the circuit. Okay, the current is not getting used up by the bulbs as it goes round. So notice that the current is the same again all the way around the circuit, but the current's getting less for reasons it will come back to later. But the crucial thing to understand for now is the current is the same all the way around. Okay, all of these are series circuits, so there is no choice. The current has only got one way to go around the circuit. Okay, crucially, you need to understand the difference between a series circuit and a parallel circuit. So here's a parallel circuit. The current comes down here. When it gets to this point, it's got a choice. It can either go through this part of the circuit or it can go through this one. So what that means is that the current coming down here, 0.18 amps, is split. Okay, because these two are the same, it's split evenly, but as you'll see, it doesn't have to split evenly. Okay, but this current here and this current here are lower. When it comes around here, it joins back up again at this point here, and again back to the same current that flows down there. Okay, a very complicated circuit over here, but you can still see the idea. 0.4 of an amp goes down there. If 0.1 goes that way, then 0.3 must go that way. If 0.1 goes that way from that, then that leaves 0.2 coming this way. When they all join back together again up here, we've still got 0.4 amps going around here. Okay, you don't have to be able to work out what all these numbers will be, you just have to be able to see that if that was 0.4 and that was 0.1, that must be 0.3. So once we've understood current, we need to look at this thing called potential difference. Often we'll just call this voltage, but if we call it potential difference, it might be a little bit clearer in your mind about what we're talking about. Potential is to do with energy, so we're looking for an energy difference. Okay, we've said charge is not used up as it flows around a circuit. So what is it that's making the lights light up? Well, what it is that the electrons that go around the circuit, the charges, but we know that in a wire those are electrons, they're carrying energy and they lose some of that energy. So when we're measuring voltage or potential difference, what we're doing is we're measuring the difference in energy between the 2 points. Okay, this is what we call the potential difference, or sometimes we're a bit lazy and just call that the voltage. Okay, it's measured in units called volts with a voltmeter. And the other thing crucially to understand again, as you'll see, is that the voltmeter has to be connected in parallel across the circuit. Okay, there's also an equation for this, which is potential difference is the change in energy per unit charge. So change in energy divided by charge. If you want to work out the energy that a component's going to give you, you'd have to do the potential difference times the charge. That might be quite hard to understand. Certainly voltage is a difficult concept for most people. So this little animation might help you. So here's the electrons, all these little circles going around here are electrons, but they're coming along with a little meter on them, a little bit like a fuel gauge. So you'll notice over here that as they're coming into the battery, the fuel gauge is on empty. They've got no energy when they're here. As they go through the battery, they gain some energy. By the time they get over here, they're full of energy. So they go round the circuit. Here they go at the first bulb. All right, by the time they've gone out of the first bulb, they've lost some of that energy, some of that fuel, if you like. So they're now half full. If we wanted to know how much energy they'd lost, it would be no good just looking at these. We'd have to say how much energy have you got when you go in, how much energy have you got when you come out. So we'd have to connect a meter between those 2 points. That's in parallel across the component. Okay, if we did the same here, you'll notice that this is going from half full to empty. So both of these would actually read the same. Here's some examples in circuits to try to make that clear for you. So we just start off with 9 volts and one bulb. Well, obviously that bulb gets all 9 volts. But if we've got 2 bulbs in series like this, the energy's leaving here. This is a bit like the animation you saw. That one's getting half the voltage. This one's getting half the voltage. Again, they don't always have to be equally split. But if this one's getting 4.5, that one must get 4.5. If that one was getting 6 for some reason, that would only have to get 3. They've got to add up to 9. Okay, in this example, we've got 3 bulbs, so they're getting 3 volts each. Okay, you notice that each bulb is getting less energy from the charges that are going through it. So there's 2 reasons this bulb is dimmer than this one. Okay, one reason is because there's less current going around the circuit, so there's less charges going through it. And the other one is that each charge is giving it less of the energy that it's carrying. So 2 reasons this bulb is dimmer. This is the circuit that normally confuses people. So in a parallel circuit, even though the battery only gives you 9 volts, both the bulbs get 9 volts. That seems like a magic trick. But if you can imagine the electrons flowing around the circuit, as they go through this bulb, any one that goes through this bulb will give it its entire supply of energy, so 9 volts. Some of the other electrons go this way and give them all the energy going that way. Okay, none of the electrons are going through that bulb and then that bulb before they get back to the power supply. They go from the power supply through that bulb or from the power supply through that bulb. So however many bulbs you have in a parallel circuit, all of them can get the same voltage that the supply is giving you. So our third quantity is resistance. We might have got a little bit of an inkling for this by now because we've seen that if you add more bulbs in a series circuit, the current goes down, but we haven't really explained why that is. Okay, well the reason it is the more bulbs are in the circuit, the harder it is for the electrons to flow around the circuit. That's why you get less current. We can put a number to that, and the number to how hard it is for the electrons to get around the circuit, that's what we call its resistance. Resistance is measured in ohms, and we usually don't use a meter for it. We usually actually have to do the equation. Here's the equation. So resistance is linked to potential difference current by the equation. Current is potential difference divided by resistance. If you look at this, what we've got is what's going to affect the current. Well, if we increase the potential difference, we'll get more current. But if we increase the resistance, we'll get less current. In symbols, I for current, V and R, the sensible symbols for voltage or potential difference, and resistance. Here's a little visual reminder of that. So here's our voltage, current and resistance. If I increase the voltage, you'll notice in the circuit I'm getting more and more batteries. The voltage is getting bigger. The current is also getting bigger. If I increase the resistance, okay, notice as the resistance gets bigger, the current must get smaller, and vice versa. Okay, you can do the maths with the numbers there. It's a little bit tricky because this is in milliamps. But hopefully that visually shows you the connection. More voltage gives you more current. More resistance gives you less current. Last little bit on resistors. Variable resistors, you'll have used these in class. So these are the things with a slider on them. The current goes through the resistor. If it has to go through all of these coils, it has a high resistance. If it has to go straight out the top, it has a low resistance. So that's a high resistance at that end and a low resistance at that end. A variable resistor, very handy thing to have when you're trying to control things in a circuit. Okay, here's a little animation to show you this down the bottom here. If I decrease the resistance, or increase the current, if you increase the current, the bulb gets brighter. So there's our nice bright bulb where the resistance of the resistor is low, but the more resistance I put in, the lower the current gets and the dimmer the bulb becomes. Loads of stuff to take in there, lots of really difficult ideas. Often when you look at circuits, it's hard because you're trying to work out which idea to use to solve it. So here's just a few questions with increasing difficulty. Try to help you to think through it. Have a look at these, see if you can maybe work out from all the rules that we've talked about what the missing numbers are, and then I'll just talk you through them. So the grade C ones start off quite easy. All we've got is to use the formula, so we know that in this case current is voltage divided by resistance, so we've just got to do 12 volts divided by 4 ohms. 12 divided by 4 gives us 3 amps. If we're trying to work out the resistance, well, resistance is voltage divided by current, so 12 divided by 2 gives us this one, must be 6 ohms. Okay, once you start to move on to this one, you've got to try to work out a few rules. So again, the first part, C here, is the same sort of idea. So in C, all we're doing is the voltage divided by the current. We've just got to be careful to use the right voltage. So we want to know the voltage across this resistor, not 12 volts because that's shared. This one's got 8 volts, so 8 divided by 2 is 4 ohms. But then we seem to have only one of the three things we need here. We haven't got the voltage or the resistance. How are we going to use the formula? Well, we can use the formula once we've noticed that this is 12 volts, this is 8 volts. We know that 12 volts must have been shared between these two things. So, in fact, this must be 4 volts. Now we've got two things because we've got 4 volts and we know that the current flows all the way through around the circuit. None of the current comes through the voltmeter, by the way. So the current is 2 amps through there, so we do 4 divided by 2. It gives us 2 ohms of resistance. Okay, over here again it looks like you haven't got enough information, but if you look carefully at what we've said, here's our voltage supply here. This is a parallel circuit, so the voltages in parallel are all equal to each other. So both of these are 12 volts. Now to work out the current through these, I can say, okay, I've got 12 volts and 4 ohms. 12 divided by 4 must be 3 amps. So this one's 3 amps. This is 12 over 6, so 2 amps. How much current's coming down here? Well, 3 amps went that way, 2 amps went that way. There must have been 5 amps coming down there. And then really stretching ourselves to this last circuit. Again, we've got 12 volts from the power supply, 8 volts used there. Okay, 2 more voltages here, but not 2 and 2, because the electrons are either going through there and giving that 8 and then using the rest of their 4 up that way, or they're going this way and giving the rest of their 4 that way. So K and L on this circuit are in fact both 4 volts. It looks like a magic trick because it looks like 12 volts in and a total of 16 volts out, but you've got to think about every individual electron. So either 8 and 4 makes 12, or it's 8 and 4 this way makes 12. Okay, so every electron is only giving you 12 lots of energy. Now we can look at these two and these two, and I can say 4 volts divided by 4 ohms. So that must be 1 amp and that must be 1 amp. And then I've got these two are 1 amp each, so I can look back over to here and work out there must have been 2 amps going down there. And then to work out 8 volts and 2 amps must give me 4 ohms there. So a lot of different rules to try to apply to circuits, and spotting which one to use is usually the hardest part of the operation.